everybody, and thanks a lot to the organizers for getting us all here in this beautiful place. Let us go back to the core collapse supernova neutrinos, which were introduced so nicely by Karl-Heinz Langanke this morning. And so basically this talk goes on a little bit on the same line as Karl-Heinz this morning, but I will try to focus on specific aspects a little bit more, and specifically aspects where the very complex modeling which is required to understand the neutrino emission from the supernova can be handled, or at least can have some connections with nuclear physics experiments. And these are the people involved in this work. And okay, so I basically need no introduction because everything was already explained nicely by Karl-Heinz. And you have learned this morning that neutrinos are continuously emitted during the supernova evolution, but still, because of the very different time scales that are involved, one can schematically, but quite realistically, distinguish different phases, different stages. A first stage which corresponds to the infall phase and the first neutronization burst, and then the long accretion phase, where the neutrinos push the shock wave and cause the explosion, and then the longest phase, which is the cooling phase of the proto-neutron star. And in this talk, I'm going to be interested only in two out of these three phases. The first and the last, and this is exactly because this is the situations where it is possible, at least approximately, to decouple the hydrodynamic problem, which is very complicated, from the underlying microphysics, nuclear physics problem which is behind. So let us start with the prompt neutrino emission. And for this phase of the process, the basic microphysics input, the basic ingredient that leads to this emission is given by electron capture. And the associated experimental program, which is nowadays already quite active to try to settle this microphysics inputs, is based on charge exchange experiments and beta decay. So why this prompt neutrino burst is interesting for us? This is because if we restrict ourselves to the first milliseconds after the bounce, the supernova bounce, even some tenths of milliseconds, then it is a good approximation to consider that the spherical symmetry is preserved and there are no complex convexities that play into the role, which means that one can model the process with the one-dimensional hydrodynamics, which is numerically much more stable and much more robust. Moreover, even the dependence on the progenitor mass is pretty much reduced with respect to later phase of the neutrino emission. And the combination of these two things means that this is a very strong case for testing microphysics. And this is not a very original statement that I'm saying. This is something that is known since a long time. And indeed, there has been many complex studies. This is from the Garchin group. There are other studies on the same type, which have tried to study how the neutrino signal is influenced by the different microphysics inputs that are pertinent to that. So in this slide here, on the left, you can see the luminosity of the different neutrino species, how they are affected by the different models for the electron capture. On the right, you can see the effect of the equation of state, which are basically the two microphysics ingredients that are typically invoked. But the point is that this dates back to 2005, and in the last 15 years, there has been a tremendous progress, both on the electron capture modeling and on the equation of state modeling, and even more on the connection between the two. That is that nowadays we know that it's really very important to have consistency between these two ingredients. And for this reason, it is important to sort of redo this kind of sensitivity things with much more modern state-of-the-art nuclear physics knowledge. And so this is what we have done. Other groups have done things in the same spirit. So this is the simulation setup. What we have done is that we are using an hydrodynamic codes, which is the coconut code that was developed by the Medon group in France. This is a one-dimensional code, spherical symmetry, but it has a very complete and sophisticated treatment with the full multi-transport scheme for the neutrino dynamics. And therefore, it is adapted for this kind of applications. And using that code, so we were able to study separately the different microphysics ingredients, trying to disentangle the different things one from the other. And these are the equation of state, the mass model, and the electron capture rates. And so this is an example of the results. This is the evolution in time of the electron fraction during the collapse. So you see electron fraction goes down because the star is deleptonizing. And then the thing is finished here at the time of beta equilibrium, where the thing got settled. And what you see here is the effect of the equation of state. There are two equations of state here. This is stiff, this is soft, but the specificity of that is that both equations of state are realistic in the sense that they fulfill the recent constraints that they come from nuclear physics experiments, from the gravitational wave signals, from the new constraints of nowadays. And moreover, both of them, they account for the full distributions of nuclei, and therefore the electron capture is consistently calculated on this full distribution. And you see that when you do these things consistently, even if there are differences in the dynamics, well, at the moment of the beta equilibrium, there is absolutely no difference between the two equations of state. The things sort of compensate, which is sort of a good news, because this means that this is a robust feature, and this does not depend much on that. There is a little effect on the kind of approximation that you do. This fact of accounting for the full nuclear equilibrium, the fact that the electrons are captured on many different nuclear species. This is this NSE. This makes an effect with respect to previous modeling that were neglecting this aspect. So this makes a little difference here, which is comparable to the effect that is given from the mass and the model for the progenitors. But by far, what really is influencing the deleptonization dynamics, this is the electron capture rates. And so this is why I'm saying, and I'm not the only one, I think everybody agrees nowadays that the microscopic ingredient, which is really important for this first phase of supernova evolution, is the electron capture rates. So what are these electron capture rates? In principle, these are things that we know perfectly well how to calculate with a nuclear structure model, like large-scale shell model calculations. The problem is that these sophisticated microscopic models of electron captures are are used for these supernova codes as tables. And those tables do not cover the whole domain of temperature and densities that is important for the capture. The latest phase here, which the most dense, it is the most important for the electron capture, and one has to extrapolate the things out of the grid where the calculations are available, which are those points. And moreover, these calculations are only available on a limited set of nuclei where those rates are confronted with experimental data quite precisely, and they're very trustable. And if you see here these arrows and these sort of things here, this is the typical trajectory during the collapse in the proton and neutron number plane. That is the typical nuclei which are met. And you see that these typical nuclei that are met do not correspond to these shaded colored areas. That is where the microscopic calculations are available. So because of that, what people do is that typically they do approximations. And the approximations typically means that instead of calculating the full nuclear structure calculation, that means considering that these electrons can be captured over many different nuclear states, not only from the ground state, but from the excited states, and they can lead to many different final states. All this is neglected and take just like a single transition in such a way that this is a completely analytical expression. and maybe we are going to have some new lamps or something. And for this analytical expression to be trustable or reliable, then the Q value, the energy of the transition energy, and the matrix element of the transition are taken like parameters that are adjusted such as to reproduce as good as possible the full picture. And so the original historical way of doing that, this is these Brun rates, where these matrix elements were calculated from the elementary shell model, single particle shell model, which implies that there is no capture beyond n equal 40 because of the gap. And this was like the standard in the 80s, 90s, and early 2000s. Since the early 2000s, the new standard is more this expression over here, which was proposed by Karl-Heinz in 2003, and which is a sort of fit of the microscopic rates. And more recently, we have proposed a slightly improved version of this fit that allows an isospin dependence to the transition energy, a density, and the temperature dependence to take into account this multiplicity of the transitions at finite temperature. And that also includes odd-even effects, all this fitted from the large-scale shell model calculation. Okay, so so we compared these three models. I'm not going to insist much on the effect on the supernova, and I'm just going to show you immediately the effect on the neutrino, which is the subject here. And so what you can see here is that these three different approximations, let's say, they lead to a quite different deleptonization rate until the settling of the beta equilibrium. And this, in turn, reflects into the neutrino signal, the first bump, which is the collapse, and the second bump, which is the burst just after the bounce. And these differences in the luminosity and also in the energy spectra can be directly understood. I'm not going to explain in detail, but they really come from the difference in this deleptonization, which is associated to a difference in the mass, enclosed mass at bounce. Okay, so this is three different models, three different results. So one can ask, well, what is the good model? Is there a model which is good? And the answer is, well, actually, no. None of them is really very good, in the sense that what is in principle good is the microscopic calculations that are constrained by the experimental data. And all those models are like fits of that allow to extrapolate these calculations to regions where the calculations are not available or the data are not constraining enough. Still, of course, something like this improved fit that we proposed, since it has more just parameters of the fit, it better reproduces the microscopic calculation. So in principle, it is supposed to be better. So the microscopic calculations are the red points, and the fits are the empty points and the lines. So the, let's say, standard fit, this is this full line, and this improved fit is the empty points. So one can say, in principle, this improved fit is improved, so it should be better. But still, if you see where this improved fit differs from the, let's say, standard fit, it is essentially over here in the very low Q value region here. And in this region, there is no microscopic calculation. So both of them are extrapolation. So this means that really, to give the final answer, one should benchmark on either experimental data or microscopic calculation, or better both. And exactly in this region. In this region, if this region is important. And what is in the important region? This is something also that we know quite precisely, because there have been different sensitivity studies. And in this case, this is from our paper, you can see that in the latest phase of the collapse, which is where the deleptonization rate is the biggest over here at the last moments, then the number of nuclei which ensure the most of the total capture rate are very limited. Some units, less than 5. So it's not so many. And even if you really want to have them all, this is some 170, which is not small, but it's not as big either. And they are all lie over here. This is our calculation. The black one is from Titus et al. The different sensitivity studies agree. And they are all around very neutron-rich nuclei, around n equal 50, and some little contribution from n equal 82 in the very last phase of the collapse. Okay, so we know where we need this data, this calculation, and the field is progressing very fast. In the very last months, there have been a very nice experimental campaign, which is nowadays done by the MSU group. I was hoping to have Remco Zegers to explain this in detail, but in any case, this is new data from charge exchange that are not exactly in the most important nuclei, but just on the surface of this important region, and that can be used to benchmark the microscopic calculation. And once this microscopic calculation, like this temperature QRPA from Karl Heinz and collaboration, are benchmarked on this experimental data, then they can be performed in regions like this nickel 78, which is really in the middle of the region, where the data don't exist. And in that way, this is very recent, of course. It has to be improved and so on, but it is, I think, clear that in a very short time, we should be able to give predictions of this neutronization of these neutrinos from the first burst, which is virtually model independent. And this, I think, is interesting because from the hydrodynamical point of view, this part of the spectrum is also model independent. So this means that would be neutrinos that can be used to study neutrinos instead than to study supernova, if everything else is under control. Like, for instance, to study the mass hierarchy, as it was proposed, for instance, here in this paper here, the difference between the normal hierarchy and the inverted hierarchy can be sorted out from the raise time of the neutrino signals because of the mixing between the different species, provided, of course, the predictions of this luminosity is very precise. Okay, so this was my first point, and then I go to my second point, which is the last phase of the neutrino emission from the supernova. This is the cooling from the proton-neutron star, and there the key physical input that determines this kind of emission. This is the composition, matter composition of the neutrinosphere, and the kind of experimental program that can be done and is already starting to be done to settle this kind of things is the measurement of chemical constants. So what is that? We are like making a sort of picture at a given point, which is some 5 seconds after the explosion onset, so after really the shock wave has gone out. And at that moment, of course, the exact moment depends on the progenitor and everything, but at that moment, you see the density profile of the supernova is very steep because you have the proton-neutron star, which is here behind. And also the temperature profile is very steep here. And here you see here in colors the neutrinosphere. And you can see that this neutrinosphere, they correspond to relatively low temperatures in nuclear physics terms. That is around 4 MeV or something. And a density, they cover really a very huge range of density. It's the surface of the proton-neutron star. And so up to saturation, but below saturation, with also a huge range of proton fraction here from almost symmetric to almost neutron matter. And in this kind of condition here, matter is not homogeneous. It's not just protons and neutrons. This we know that there are going to be clusters, light clusters. And this means that, the interactions of neutrinos over here, they're not happening on free particles, but they are rather happening in interactions with the light clusters. And it is this kind of processes that are going to be the main source of the opacity at that moment. And so they're going also to give the initial condition for all the nucleosynthesis processes that were described this morning. So, okay, this is easy again because in principle, this composition is again something that we know very well how to calculate. This is statistical mechanics. We know pretty well if we know the temperatures and proton fraction, blah, blah, blah. This is very easy. The point is that it depends on this effective mass. And the effective mass in turn depends, of course, on the binding energy of the particles in the medium. And this is not easy because this is many-body physics. And so at that point, there are models. There are different models that predict different modifications of the binding energy of the light clusters in the medium. And if you consider these different models, you can see how they affect the abundances of the light clusters as a function of the temperature and the density. You can see that depending on this medium modification, the density at which these clusters melt down in the dense medium can be modified. And so in the region of interest, you can have either like 70% or 0% of those light clusters. So this can change quite a lot depending on this medium modification. So the point here is to try to experimentally pin down how the binding energy is modified of these light clusters in the medium. And the proposition, which was done some years ago by the Texas A&M group, was to study that in nuclear multifragmentation, because using this observable, which is called the chemical constants, which is basically particle densities of different clusters, but properly normalized in such a way that the effect of these medium modifications to the binding energy is pretty important. You see here, without the medium modification and with the medium modification, this changes the observable quite a bit. And recent experimental data from the Indra collaboration here on these chemical constants for the different light clusters. And they are compared here to our relativistic mean field calculation, where we can include this medium modification in a completely phenomenological way by adjusting the coupling to the scalar meson with the constant, with the reduced coupling, and which can be fitted to the data. So again, this is something which is new. It's something that has to be done in a more extensive way on more systems and so on. But in principle, this is a way to get this value of this binding energy in the medium, and therefore a very precise calculations of the abundances close to the neutrino sphere. And that's all. So I try to give you a hint a little bit of in how nuclear physics experiments, and of course the theory that allows to interpret them, can have a real impact in the modeling of the neutrino signals in the core collapse supernova, at least in some parts, because there are this accretion part that really depends on the complex hydrodynamics, multidimensional hydrodynamics. And so these are the two parts where really nuclear physics is important, collapse and neutronization burst. This is essentially governed by the electron capture rates. There is still some residual model dependence. It's getting smaller and smaller, and it's going to be benchmarked on experiments and calculations on some well-defined sensitive nuclei. And then the second point is the early proton-neutron star cooling phase, which gives also the initial condition for the nucleosynthesis processes. And this needs a reliable modeling of the composition close to the neutrino sphere. And there, the hint is given by the cluster abundances that can be measured from heavy ion collisions to settle the medium binding energy shift. And that's all. And if my chairman gives me 30 extra seconds.
Please.
Yes, please. So I take the occasion to give a little announcement, which has nothing to do with the conference, but maybe it has something to do with us here. It has to do with education and networking about education. So it is an announcement about this Erasmus Mundus joint master degrees in nuclear physics that is the only master degree in Europe which has this Erasmus Plus label, let's say. We've been recently this year renewed for 4 extra years. The program is, the applications are open now. There are 15 Erasmus Plus scholarships which are available. I think it's still 15 days before the call closes. So if you have students which are interested in this exciting European experience, getting all around Europe to get your master in nuclear physics, please come and see me, or just note the website, and thank you. That's all.